And hello, welcome back. We're gonna continue our discussion into the IDDES model. First, we're gonna talk about what wall model LES looks like. So, especially for the Spalart Allmaras adaptation of it. Okay, so we were talking about length scales and blending. So again, the blending function is FB over here. And this FE here, 1 plus FE to be more precise, this is here to control the log layer mismatch problem. So that's what it's there for. Okay, so FB is quite straightforward. FB equals 1 is in Rens mode, FB equals to 0 is in LES mode. Okay, so this is what FB looks like. It's a minimum of 2 times exponential of something in there, then 1.0. So FB will range from 0 to 1. So you have this 1.0 here to keep FB purposely between 0 and 1. And you know, exponential cannot go below 0. So that's why this is actually pretty useful. This exponential function is pretty useful. So on the whole, this will range between 0 and 1. That's what this min 1.0 and this thing is here for. Now the more interesting thing is what alpha is. Alpha is a function based on a constant here. Yeah, the constant here, but more importantly, this is the distance from the wall, d, w, distance from the wall. And Hmax is this cell size. Okay, so Hmax equals to the maximum distance of, you know, your cell volume, your block. We have Hx, Hy, and Hz. Okay, that is if your cell is in a cuboid kind of a configuration, or they call it orthogonal. Okay, so it looks like a rectangle, 3D rectangle kind of thing, then you can use this kind of definition. If not, if you have a very unstructured cell, if you have a cell that's really oddly shaped, you cannot use this definition as well. But this Spalart Allmaras DES model, or rather the wall model LES model, it was developed with the assumption that you have an orthogonal grid, meaning to say a grid full of rectangles, squares, a very orderly fashion looking grid, where all the angles that you see are all like 90 degrees, right? So the angle between the grids are all 90 degrees. This is what it was designed for, or rather that was what was discussed in the paper. Okay, so this is actually a function based on, okay, the length from the wall and the cell size, and that helps to blend. Of course, the further you are away from the wall, of course, then you will switch on your LES a bit more. Of course, you have a Hmax here, you have the cell size dependence there as well. That will control, of course, your grid, your subgrid viscosity scale. But that's how they do this interplay between Rens and LES. So this is what the blending function is there for. Pretty straightforward. So what's FE here for is to help with the model stress depletion. Well, as a phenomena that is based on this model stress depletion. Again, where you have a drop in the turbulent viscosity and it's not being made up for by an increase in actual resolved turbulence. Okay, where you have all those eddies in your velocity field or resolved velocity field. So this one isn't exactly grid dependent, but it causes this log layer mismatch. So what is FE here for? It is to help with this log layer mismatch, which is caused by model stress depletion, like I was explaining in the earlier video. So what do we want FE to do? We want FE to be 0 at all times. Okay, we want FE to be 0 at all times, otherwise it messes up the model. Except when it's here to correct this model stress depletion or this log layer mismatch. So it is here to make up for the it's here to slow down the eddy viscosity reduction. Here to slow down the eddy viscosity reduction from the Rens model, so that LES has enough time to so-called generate the turbulence. Okay, there'll be enough turbulence inside the law region of the boundary layer to kind of take over. Okay, so what do we have? We have FE looking like this. FE equals to the max of, again, FE1 minus 1 and 0. So this actually kind of limits FE between, yeah, it prevents, okay, this 0 here, it has a floor, it's a minimum value, so you want the maximum of FE1 minus 1 and 0, so that you will have a function that will not go negative. Okay, it will not go negative, and it's controlled by two other functions here, FE1 and FE2, and then you have psi, this psi coming from making a comeback from the low Reynolds number correction. It is exactly the same psi, but what I want you to know, and it was written in the paper, what we are doing here has nothing to do with the low Reynolds number correction, at least conceptually speaking. Okay, so conceptually speaking, okay, conceptually speaking, has nothing to do with the low Reynolds correction. The concepts are completely different. It's just a convenient function to use, and it exhibits the correct numerical behavior. So because the thing is that it's convenient to use, therefore just use it. You don't want to reinvent things and make things a lot more complicated. So everything in here is the same things as was discussed in the DDES models. So I'm not going to go through that. The only new things are this FE1 and FE2. Alright, so again, remember the whole intent of having this FE here is to slow down this model stress depletion and make sure that your eddy viscosity does not deplete to such a point that your resolved LES eddies cannot make up for this turbulence, equivalent in turbulence. So it should make up. So there are a few ways to slow it down. Okay, one way is to preserve the Rens eddy viscosity based on length scale. So this is what FE2 is like. It's 1 minus, again, the max of FT and F1, or FL, sorry, it should be FL. Okay, so FT is some hyperbolic tangent function, and so is FL. T over here actually stands for turbulent. L actually stands for laminar. Okay, T stands for turbulent and L stands for laminar. And then you have a CT here and CL here, which are actually model constants, which you kind of just have to calibrate. If you want to take a look at what some typical values are, you can take a look at the OpenFoam turbulence model, the Spalart Allmaras IDDES.c. Okay, line 66 to 78 provides a formula, line 208 to 205 provides the values. Let me show you where they are. So 68, line 68 onwards, you will see these two functions here. The hyperbolic tangent, power 3, POW3, this is the cube root. Okay, power 3, square root of, okay, whatever is there, CT times RD. Okay, so what is that? Okay, so you will have CT square times RDT. So this is the cube root power. So CT square is here. So you square CT, sorry, it's not square root, it's square of CT. And so this CT underscore, this is what you basically want to look for in this code, and then you can look up the value. And then you also have this CL, and it's also inside the code here. You will see you'll see this one over here. You will have this one I'm highlighting, hyperbolic tangent. This is how it's applied in OpenFoam. Hyperbolic tangent power square CL times RD, okay, blah 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 blah, and then power, and then you have the argument 10, which is raising it to the power of 10. So this is raising it to the power of 10 here. CL is here, is the laminar constant. The places which you find it are in lines, at least in this version, line 208 to 224. Okay, CL is 3.35, so let me write that down. CL equals to 3.35. CT equals to what? 1.63. These are just model calibrated constants. I mean in OpenFoam they are already default values, so you don't have to change them. If you want to, you can, but if you're not sure what to do, just stick with the default values. Yeah. So that takes care of these constants over here. Now what are RDT and RDL? Or what is this thing here? So recall from the Spalart Allmaras Rens model, we have the RD as such, or maybe you have over here the mean rate of strain tensor. Well, it's not exactly the mean rate of strain tensor, you kind of modify it over here. But okay, the one we work with, at least here, it is this version. You have nu t plus nu on top. Nu t plus nu on top, then you have the gradient of u, the magnitude of the gradient of u at the bottom, the von Karman coefficient, and then you have this distance from the wall d. Over here we use the notation dw. dw or d is the same thing, okay? Distance from the wall. Okay, to make it more numerically stable, okay, we make sure the denominator doesn't go to 0. Alright, so what is more likely to go to 0? It is this delta u, right? This delta u, this magnitude of delta u can be 0 in some cells, but dw will not be 0 in pretty much any of the cells, if I'm not wrong, because the cells, there will be always some finite distance from the wall, even at the wall itself. So you have a wall here, you have a cell at the wall, you will have the center of the cell at some finite distance d here, right? And it will not be equals to 0. Yep, it will not be equals to 0. So you'll hardly have this problem, because RD is calculated for each cell, and D is actually the central distance from the cell. Distance from the center of the cell to, let's say, the wall. So D is not equals to 0 in this case, because you always measure from the center of the cell, so that should not be a problem. The only problem is this, and you kind of want to get a max function here, just to make sure that it doesn't like go to 0. So you have a max, okay, 0 and this, okay. So that's all you're doing here, okay. So let me get rid of this then. You don't really need that anymore. Okay, so what's RDL and RDT? Okay, RDL is basically just the laminar part of this RD. You define it like so. You have the laminar part of RD, which is just as such. You just take this out, the turbulent part out. Likewise, RDT is pretty straightforward. RDT is pretty straightforward. It's the same denominator, except that you just take the turbulent part of the viscosity, effective viscosity. Now what does this actually do for you? This actually makes FE2. FE2 actually controls the descent of Rens eddy viscosity based on the viscosity scale, or based on the viscosity here. So FE2, okay, controls drop in eddy viscosity based on nu t. That's the basic idea. Of course, there are some dependence on the wall distance and what have you, because RD is after all dependent on the wall distance and the eddy viscosity. But the main idea is that it controls it based on the eddy viscosity. Alright, it controls the rate of the switch from the Rens model to the LES model based on eddy viscosity. In fact, it's very quite similar to our DDES model. So no problem over there. So that's WMLES for you. Alright. So what is next? Okay, so this the wall model eddy viscosity, where you want it to simulate using the Rens model in the inner boundary layer or the viscous boundary layer, and then the turbulent boundary layer you want some LES, which is a bit different from DDES. Okay, so hopefully you know what this WMLES does. Okay, and it's all these things. At least you can get an intuitive sensing of what these functions are trying to do, without going too much in detail how you derive them or why you derive them as such. Okay, the next thing, of course, for IDDES, the core idea is to blend these two approaches together, the WMLES and DDES models. This is the key change for IDDES. So the basic idea is to blend these two length scales. So remember, we just gone through the length scale of WMLES, and this is the length scale for DDES. Alright, you have this FD over here, which is the delay function to prevent the onset of LES inside the boundary layer. Okay, for DDES, but for WMLES it's slightly different. So you have a blending of these two length scales. Now, how do you combine them together? Well, in the paper you will see that you actually modify the original DDES length scale. Alright, you modify your DDES length scale so that it will look like this. Okay, so first thing first is that you want to blend between this FB and this FD over here. So you have this FD tilde, alright, which will switch between the Rens model and the LES model. And inside this FD tilde you will find this FDT, which actually helps, it's more representative of, let's say, the DDES part. FB actually comes straight from the wall model LES model, and this FDT here is 1 minus the hyperbolic tangent of 8 times RDT to the cube. Okay, so this is 8 times RDT to the cube. Alright, so that's what was presented in that paper. Okay, this should be equation 16 if you are taking a look at the paper, but yeah, anyway, this is copy and paste from the paper. Yeah, so you have this RDT here. Well, yeah, okay, so just a note, in the code itself, let's say the OpenFoam code, every time you will not see a differentiation between RD and RDT. For example, over here, when you have this FT being calculated and FL being calculated, instead of RDT and RDL, you just have RD in both of these. Probably the reason is that in the turbulent, regime. Okay, never mind. Sorry, you have this RD over here. You have the min and max functions over here. So RD here is not a straightforward calculation. There will be a min function and a max function. So it kind of gets differently applied in the code. Okay, but anyway, this is what was in the paper. So this FDT is 1 minus hyperbolic tangent 8 times of RDT. And likely the reason why you can just use RDT and not RD is because I think, well, FDT is supposed to this is okay. Oh, never mind. I'm not going to. Yeah, I think this is just an empirical function, and yeah, we'll just leave it as that. This is I'll just see what this is purpose for. RDT is based on the turbulent viscosity as well. So you have the functions switching on and off based on the turbulent viscosity, length scale, etc. to switch between the Rens and the LES model here. Of course, where you'll see the DDES is here, you'll see the WMLES is here. Alright, and for WMLES, you also want to combine this FE function to prevent this, what do you call that? To prevent the wall model model stress depletion, where your new T goes down too fast as a result, and your LES doesn't really catch up in the resolved turbulence bit. So you have these models over here. So this is what they are. L tilde IDDES, the length scale will be as such. Okay, the behavior discussion, we can discuss the behavior as follows. In large resolved turbulent inflow, this RDT will be much less than 1. Because remember, what is RDT? RDT is this. Okay, RDT is this. When you have a very large resolved turbulent turbulence in the inflow. Okay, turbulence in inflow. This new T will be pretty small compared to, let's say, this over here. Because when you have large resolved turbulence, that means the turbulence is mostly in the velocity field rather than this subgrid viscosity or turbulent viscosity. Then this quantity will be very big as compared to this. Therefore, this RDT will be very small. So you have a low modeled eddy viscosity, which is nu T, compared to the strain rates or the velocity gradient, which is delta U or nabla of U. And strain rates are huge in resolved turbulent flow. Because remember, when you have resolved turbulence, you have these eddies and then the velocity is changing very rapidly. So the strain rates are very big. Okay, or the velocity gradients are very big. Okay, so just again want to stress that resolved means that you solve for the velocity field in the CFD code. You can see these velocity fields rather than you model the turbulence, okay, or model the turbulent velocities. So with RDT much less than 1, this thing actually goes to 0. When this goes to 0, this whole hyperbolic tangent actually disappears. It goes towards 0, so that 1 minus FDT, this function actually approaches 0. Okay, that triggers the FD tilde function, which is what maximum of 1 minus FDT and FB. And seeing how 1 minus FDT will go towards 0 and FB is actually any value between 0 and 1, you will most likely pick FB. Okay, you'll most likely pick FB, and this corresponds to WMLES. Okay, so you everywhere you see FD tilde, you replace it by FB. Okay, you replace FD tilde, you replace it with FB, so you will get the WMLES model activating when you have large resolved turbulence in the inlet, okay, or in the inflow. Okay, so this is where your WMLES kicks in, because you have enough resolved turbulence to take over the turbulence viscosity, the role of turbulence viscosity. Okay, so there's a good balance there. Otherwise, if FE goes to 0, it triggers the DDES models. Okay, FE goes to 0. How does FE go to 0? Okay, let's check FE again. Okay, FE is based on this, and that's based on FE is over here. It's based on FE1, FE2. FE2 is based on this RDT and RDL. Okay, so it's a bit complicated, it's very hard to see, but just remember FE is supposed to be 0 everywhere except in the place where you want to account for this model stress depletion, especially in the turbulent boundary layer. Okay, so yeah, so they have a complementary function. They behave such that If there is not enough, okay, not enough turbulence in inflow or in the flow, okay, resolve turbulence in the flow, Fe goes to 0, it triggers the DDES model. So that pretty much activates the DDES mode, and that sums up how IDDES blends between the WM-LES, the wall model LES, and DDES models. So yeah, and it's one of the more successful models used in aerospace industry, and it can be used for a variety of flows as well, seeing how robust it is, switching between models in the in a boundary layer. And yeah, it's based on a lot of tweaking, as you have seen in the last few videos. It goes from the LES models, the Reynolds average Navier-Stokes model, you combine them, you tweak them, you make more hybrids of them. It gets really complicated. In fact, it's a lot of math. Even the authors of the paper say it's getting really complicated, which is definitely not the intent. But for other comments and more details, you can always take a look at the paper. It should be free for download. But that pretty much sums up what the Spalart Allmaras IDDES model is about. So thanks for watching. I'll see you guys again next time. Bye bye.